Juan parla anche spagnolo, quindi un po' mi capisce. Allora, Juan l'ho incontrato nell'Università dell'Oregon qualche anno fa, dove era un'università che, per capirsi, con Luciana, quando siamo arrivati lì, ci siamo sbagliati, pensavamo fosse una città, è l'Università dell'Oregon. Sono 120.000 persone, tra studenti, lavoratori e tutto quanto. Poi si è trasferito nel Tennessee alla Oak Ridge National Laboratory. Per farvi capire cos'è Oak Ridge era uno dei 3 posti assieme a Los Alamos e un altro che non ricordo quale fosse, dove hanno sviluppato la bomba atomica. Oak Ridge sono 6.000 persone, completely state funded, e che lavorano sia dal plasma che dal... Davide, resta a portata in mano. Dal punto di vista, come vi ho scritto qualche giorno fa, dal punto di vista dell'interesse, diciamo, nostro fisico, il paper fondamentale è stato scritto nel 99 con Mac Williams, dove praticamente cancellando il wind stress e spingendo le correnti solo col white capping delle onde, hanno praticamente ricreato la circolazione mondiale, proprio tridimensionale. Quindi questo è l'argomento sempre che discutiamo ancora. Con lui abbiamo fatto un articolo assieme sull'effetto delle gocce d'acqua, delle bolle che vengono create sul mare, l'effetto sulle onde. E oggi ci parla sulle wave current interaction e sull'appunto wave generated transport, ma ieri sera a casa, perché è stato ospite mio e di Luciana, abbiamo parlato molto anche di biologia, perché lui fa anche modelli matematico-fisici con i biologi e cose del genere. E quindi mi sarebbe piaciuto che potesse stare di più in istituto, solo che alle 12:30 il treno per Trieste e quindi 11:37 il bus, il motoscafo ultimo. You got everything, right?
I think so, yeah.
Okay. So,
yeah.
Please go ahead and try to speak a bit slowly so everyone can understand. Ma molto slang.
Scusami, Luciana faceva notare che si vede il quadratino lì, puoi minimizzarlo per quello della riunione in Teams? There we go. Thank you so much.
You understood everything.
Yeah, I did. But by the way, I'm an Italian citizen, but I don't speak Italian. I'm also American citizen, but I am Italian as well. And thank you, Luigi and Luciana, for having me. They're great friends now, and so glad I met them, and I can come to your beautiful city and your great institute. So they asked me to speak slowly. I will, but I'm also going to be very informal. Instead of showing a whole bunch of equations, what I want to do is to make sure that I convey what's the intuition. I think that's the more important thing. The rest is just mathematics.
Well, of course, you can say that everyone can interrupt you any moment.
Of course, yeah. So I'm going to be actually flipping through slides, so it's going to be very messy, but it's because I want to get the intuition right instead of showing you I would actually do it on a blackboard or whiteboard, but we don't have one here. Okay, well, let's see. So let me get to the following. So the basic idea was the following, is that what we wanted to do was look at how particles move in a fluid flow, and in particular how they move, for example, if they were moved by waves. And of course, because of waves, they move, in a mostly elliptical fashion. If you have braking, then a thing is not going to be so elliptic. It's going to be a very messy thing. But we weren't actually interested in the paths themselves, but basically in the transport, right? So the first thing you have to say is, well, how do we actually cancel out the stuff we don't want to from the stuff that we do? And so now what we do is we think of two things. One is that we think in a multi-scale thing. There are motions that are very large over time, motions that are shorter or smaller over smaller times, and so on and so forth. So the basic tool is just simply to average, right? So just like in turbulence or anything else, what we want to do is take a path, think of it as composed of different scales of motion, and then have some filter at all of these scales to pull out what we want. Is that working? Well, they're not going to be able to see on the, they see the.
You needed to show something.
Okay, yeah, I guess so. Okay, so that's sort of the idea. This is a horrible, messy thing, but you can see, you know, I put in a big scale thing, a smaller scale and smaller, and so on and so forth. Now, the other thing that happens now, this is mathematical. So you might average everything out and you get sort of a mean flow. But it turns out that if you have, and this is from a partial differential equations perspective, if you have something that obeys hyperbolic equations, waves, when you average, you still get waves. In other words, if you average at any scale you do, the filtering still generates waves. That's not the case if you have other motions. You might be able to get other things out of different equations, but the hyperbolicity of the equations, if you use a wave average, remains at each one of the scales. Okay, so that's the other ingredient, that's the mathematical ingredient. Okay, so now let's go to town. So what we want to do is we want to say, okay, let's look at the simplest flow. And we have some differential equation that basically tells you how the particle moves with respect to a velocity. And the classical thing to think of is that if it was infinitesimal waves, meaning sine waves, right? Then the sine wave basically will have this sort of repeating elliptical motion. Nothing very interesting there. And if you average out that the wave, you get nothing. Okay? Basically, this thing doesn't move anywhere. Now, on the other hand, if the particle motion is such that it doesn't close, which is the case in water waves, then what happens is this little non-closing here over time is going to accumulate, basically. So you average out the wave and you get, so let me try to do this. You go there, and then you go there, and then you go there. And so what's happening is something is moving, as you can see, okay? Now, this is a very, very clean situation, but essentially what we're going to do is we're going to say, if we average this thing out, we have a residual flow, which we call a current, okay? So now we can say if these waves have a residual flow, they produce a current, and that's what we call the wave, that's what we call the Stokes drift is a common name for it. But in general, it's just wave generated transport. So that's the intuition. And to see that it actually happens, the famous Caltech, these are little fish scales, I guess, over photographically showing that in the various, this is a wave tank, and you can see, for example, here, the classic elliptical motion and non-closing. They just open the photograph for a period of time, shut it off, and you get these traces. And this depends on, this is a progressive wave. And as you get more into a standing wave situation, you expect the motion to stop, basically to not generate flow, because after all, the water doesn't go out of the tank, right? But if it's progressive, then you get those situations. So these are very, very clean looking waves, all right? And so you do get that classic elliptical pattern, but it doesn't close. Okay. So far that's how essentially generate waves. Now we get into the mathematical thing, and I don't want to dwell too much on the mathematics, so I'm not going to. But what basically we're doing is we're doing some averaging, this phase averaging business. We're going to pull, we're going to talk about some asymptotic limits that we're interested in. So we're interested not in very, very short spatial temporal scales of the waves, but at scales that are larger than those, okay? And then we just follow the consequences of taking this is the most generic equation you can think of. This is, it has Coriolis in it, it's got dissipation of some sort, buoyancy, and so on and so forth. You stick all those ingredients and see what comes of it. And what you're going to get, after you average out things, is you get a current, which is, let's call it the current that is imposed on the whole flow. And then you get another current, which is, I'm calling U Stokes here, but it's that wave generated transport. The vorticity also is the standard one. Now if we're talking about Stokes transport, which is just simply progressive waves, we're not going to get any contributions to the vorticity. But basically, how do you compute this thing is you take an average of this integral here, and you get that wave generated transport. This is just simply the recipe you follow mathematically to do this, and that recipe you can do it also experimentally, and you can get that as well. All right, so that's essentially the thing, and the question is, is there such a thing as wave generated transport? Is it affecting very large scale circulation? And the answer is yes. And the way it's doing it is actually imposing, if you look at just the Earth-like or Earth scale currents, you have another component which is wave generated. And so this is what we call now the wind driven circulation. We call it now the wave generated or wave driven circulation. So that was basically the paper, okay? Now, we worked out all the theory, it doesn't matter here, but if you take the theory and you just make it the simplest possible situation, you say, well, can I take data and see how what looks to be the wave generated transport at the global scales? So what we did is we just, computed equine transport. It's just basically, you get the usual equine transport here, but then there is another transport term, which is the wave part, and there it is. And essentially, the transport is proportional to the wind itself. So if you computed the Ekman transport with this climatology, so this is data accumulated over a certain amount of time, what you're going to get is this flow on the northern hemisphere, right? And what you do is if you use, as I said, this simple equation and compute this term here, we know how to do that, then this is the contribution. This is the contribution due to the waves. So this is the wave generated transport, not surprising, where it's very windy. There's also a lot of very strong waves. But notice the scale, by the way, it's a little exaggerated here. This is 0.5, this is 2. So, this is, I don't mean to falsely advertise the strength, but basically it's a small component, but it's a non-trivial component. And as you can see, the alignment is interesting enough such that it's not non-trivial alignment, so it does make a big difference. Okay, now the phenomenon is, and these are correct. You have to also correct the pressure as well, and so this is showing you how pressures need to be modified in order to include the wave generated transport. So the pressure is modified, the velocity is modified. Now, if you're an experimentalist, you went out to the ocean and measured the transport or the current, you wouldn't be able to discern what part is the wave part and what part is the current part, right? So, but this is telling you how do you distinguish that if you were to do that, right? Okay. So it's not like a new phenomenon or anything. It's just explaining something that's going on. All right, I'm going to skip all this. And then we say, okay, well, what we want to do is we want to go, let's keep going on this thing. Let's not consider something clean. Let's say, what do we do about wave breaking or anything like that? We're averaging. We're not interested in dynamics of the wave breaking, but we want to be able to say, well, I want to include the mechanism or whatever it is on the mean flow that the wave breaking does, okay? So again, without going into mathematics, what we do is fairly simple. So we go back to our little toy problem here. But now this first order, this is not the model for the equation, but this is just a thought experiment of how you would model wave breaking. You'd say, well, before I had an equation which is fully deterministic, what I could do is I could model the effect of wave breaking as a diffusion term. So this is a stochastic differential equation. Now, this is a continuous diffusion term. You might say, well, the breaking only happens at the surface, so maybe what it should be is something more like a Poisson process, Livy process, whatever it is, fine. But basically, I wanted to give you sort of a way to think about how to incorporate wave breaking into the dynamics, and you do it by adding a random term, and you have it blow up every once in a while, and do it over time. But essentially, what you're introducing is uncertainties now in the current. Okay, How does the uncertainties play off? Mostly by dissipating, by making it less effective transport, right? So it breaks, so there's less transport. But you say, wait, maybe that's not quite. Maybe there's more transport. It's not clear whether you should get more or less. Okay, so this is not going to tell you that unless you tell it what to do, it won't know what to do, right? But it's a way to think about how to include naturally transport. And so I wrote a paper that no one ever cites, but this is a long time ago, in which I said, well, this is one way you do wave breaking, as opposed to other people who basically sort of throw it in there. You just tell nature to do that, and it'll break, right? It's just a model, okay? All right, now, what happens when you include, for example, so this is actually from CFD calculation. So it's a complete, Navier-Stokes calculation of you put a particle in the flow very close to the bottom of this tank, this numerical tank, and you want to see what it looks like when you have waves. So this is a code that actually can have a free surface, it gets waves, and you say, well, I want to see what exactly happens. So if you have clean waves, you get something that looks like there's dissipation. It's Navier-Stokes, right? And it's in the boundary there. So this is the classical elliptical path, very close to the bottom. And then if you make it more interesting, you get really messy looking patterns, right? So the moral of the story here is that our elliptical toy conception is completely messed up, or it looks a lot more interesting, for example, when you try to, this is a case in which you make wave breaking occur, wave breaking in a very soft sense. This code does not break. It just simply makes very, very steep looking waves. And you want to say, okay, what does it look like? And it's pretty messy looking, okay? So this one actually does a hell of a job of transporting, this one doesn't. But it turns out we can also make it, so transported between here, I don't know where the end is, maybe this one. So this went from here to here, and here it went from here all the way over here, right? Now, but we can also make this the opposite. We can make it transport very far. And that's if we have wave breaking in the true sense, okay? So that's the next step. Okay, so that's what we call, this is all this stuff about Longuet-Higgins, who was brilliantly described essentially, well, he revisited the work of Stokes and other people, but he actually worked out very generically what wave generated transport is. It's a mass transport equation in 1953, which is worth looking at. He was very, Longuet-Higgins was very idiosyncratic. He derived everything from scratch. He never looked at the literature for anything. But that paper is very seminal. And he also derived the radiation stress, which is the one that produces this longshore current, right? It's the same radiation stress. It's the same thing that we're talking about here, okay? Radiation stress is the same. We have something, Jim and I have something called the vortex force formulation, as opposed to the radiation stress formulation of getting waves and currents to work. That has to do with technicalities of how complete you describe the fluid flow, from pressures to velocities to currents and everything else. And so we quibble about corrections and so on and so forth, but these are all different versions. There's another version called the generalized Lagrangian mean flow, but we all are talking about the same thing. Okay, so now that I'm being so informal, I don't know where the hell to go, but we've done the following. So now you have an intuition as to what it is that we talk about when we're talking about wave generated transport. Is just simply filtering out the wave, the phase, and looking at what happens after. The second thing we've learned is that if the waves are progressive, you're going to get transport. If your waves are standing, you should not get transport. You don't have the stuff, pull out, so there's no transport, and that indeed is the case. The third thing you get out of this thing is that, yes, under progressive, nice, clean progressive waves, the orbit is elliptical. But now when you start considering either taking a tank or an ocean, just moving it, shaking it, then you're not in the elliptical range, you're into something else. And this happens either if there's wave breaking or no wave breaking, okay? This is what we contend with, and from this, we eke out, for example, nice clean things like that. Okay, so far, we're okay. The rest is mathematical stuff to make everything work out. Okay. Oh, and then the last thing we learned so far is that the theory is not showing you a discovery of a new current or anything else. If you go out in the field and measure the ocean currents, what it's doing is it's telling you what aspect of this is wave generated and what part is not. That's the key thing. Okay, now, so these are different models for, this is what happens if you use different noise models for wave breaking. You get different orbits, but okay, and I don't want to go into all this, but if you have wave generated transport with breaking, you get all kinds of different terms. It's going to affect not only the velocity itself, but it's also going to affect the pressure. It's a very complicated thing, but this is just sort of mathematical turning of the grind of doing this averaging procedure when you have stochastic differential equations representing the velocity. Okay, so let's not go into any of this. Oh, these things are not going to run, so I'm not going to bother with it. This is to indicate what happens if you have wave breaking and you're looking at particles on the surface. I forgot to download this movie onto this computer, so I can't run it. So let's skip that. This is, okay. So the next step is, well, where is this? What happens in the deep water is something that we considered in the 1999 paper. So that's basically basin scale circulation. And essentially, you are modifying the wind-driven part. And now you say, well, where is this effect really important? And so you start getting closer to the shore. Now, closer to the shore, what we call shallow waters, so basically cases in which the wavelength is very long compared to the depth. In those cases, this wave generated transport becomes more important. And that's where we sort of started focusing our attention. So if you look at regional ocean models like ROMS models, these things already have this vortex force in it. They all have it. And so I think some of the global circulation models are starting to put it in as well. But basically, this is what's showing you what happens to a vortex. This is just the vorticity contours. This is when you don't include the wave generated part. And as you can see, the effect is when you include the wave generated part, you get, these are at the same time, this is two different realizations of what happens. So the effect is much larger in the shallow water depth. Okay, so now, what do the equations look like in a shallow water situation? Let me see, where is it? I have to go all the way back here. Oh, where is it? Okay, I'm gonna have to resort to just saying it instead of showing you. All I was gonna do is show you a bunch of equations. Okay, so I'll tell you what happens. I'm not gonna find it, okay, so in the shallow water limit, as opposed to the basin scale, in the basin scale, you essentially have the wind generates waves, the waves generate a transport, the transport actually modifies a quasi-geostrophic flow. So it's a sort of a one-way, and then what happens when you get into the shallow zone, then you have a two-way interaction. So now you have the waves generate a transport, modifies the currents. Okay, so you get the longshore currents will be modified. But now the currents will affect, among other things, it will cause a Doppler shift on your waves, among other things, because you're moving these waves. But the other thing it's going to do is it's going to modify the amplitude, the slow modulation of the amplitude of the waves, which are captured by what we call wave action equations, essentially the evolution of wave numbers and amplitudes. Okay? So you have, when you work out the situation for the shallow water limit, you have to get longshore waves, get a pumping, and you'll notice that only very, very close to the shore. The second thing is you get the quasi-geostrophic flow itself gets modified with this Stokes drift type term. And then finally, equations of the currents modify the equations of motion of the wave number and amplitude of the waves by actually introducing into them Doppler-like effects as well as effects of either focusing or defocusing. Okay, so that's essentially what happens. Instead of showing you the equations, it basically shows you a bunch of equations that couples three things: waves, currents, and longshore waves. Okay, all right. So what I'm going to do is tell you something that's new and maybe something that experimentals might be interested in doing. And so I'm going to convince you, and this is not done, no one knows anything about transient transport. Everybody's worked out Stokes flows and all these other things, fine. So what happens when you take an ocean, you just suddenly shake it? What do you say about transport there? And that actually is very, very impactful transport, right? So suppose you have a hurricane, right? It's going to shake the situation really hard. It's going to generate a tremendous amount of transport, and that cannot be captured using this Longet-Higgins idea. We're out of the regime in which we are able to actually choose. And what we did is work out how it is that you work out use cases in which you have, you're not talking about small displacements of the particle motion, but large ones. Okay, that's the new thing. And I'm hoping that experimentals might find that interesting. It's, for example, what puts flotsam and jetsam very quickly onto the shore or removes it very quickly, you know, stuff like that, right? Okay, so now it turns out folks in Scripps developed a numerical wave tank that looks like so. It's a tank that has water and air. It has a free interface. It's got a sponge layer at the end, and you can basically throw progressive waves down this tank. And this is time and this is space. This is a progressive wave going down the tank. And this is a non-breaking case. They can actually make this thing break. Okay, so numerically breaks. So this is a group.
Is that paddle generating?
Yeah, so you put in, and numerically you put in a paddle, a function here onto this. It's not a Navier-Stokes solution, but something close to it. And then you see what happens, but it allows the particles to actually break off of the free surface, and it sort of models wave breaking. This is by Luke Dykey and some other folks who have generated this code. Luke Dykey now is at Princeton. Okay, so we are taking, this is data. When we say data, we're talking about numerical data, okay? And so this is where we actually capture data. This is just showing you that under this very, very fierce looking wave, we're going to take lots of data and everywhere else not, okay? And this is just a typical profile of a non-breaking but pretty intensely nonlinear situation, okay? All right, now let's see if this is going to work. So I think I'm supposed to go here. And then, let's see. Okay, I don't know if everybody can see it at home. All right, and this is the free surface. And there's the wave that's coming in. And in fact, it's a wave break situation. So it's all numerically generated. Okay. Now, if we look at the particles underneath them, see if this works. So now we're looking at some particle mode. We just pick some locations and look at how the particles go. So they're kind of doing this elliptical thing, right? All right. But as you can see, some of them are hard, you know.
Can you show it again?
Yeah. This is not the best example, but so I wanted to, let's see. Okay. So mostly what you see underneath is the classical, this is a very clean looking wave, but it breaks, right? It breaks because it's steep, it's very steep. And so what you're seeing is below, you still get kind of the elliptical thing, but if it's very, very close to the surface, you don't. But more or less everywhere else you do. Okay, that's basically what it's showing. So one last time, and then, oh, up. Okay, now what they meant to contrast was this to this. All right, and so they were working with us, but they split off of us. And they were very quick to write a paper, and they basically said, well, what does wave breaking do? It actually produces a lot more transport. And the answer is yes, but so they were a little too quick to publish. But anyway, so what we did is we said, no, let's actually try to see if we can understand transport in this transient situation. And so let me go back to, where's my talk? This one. Okay, that's that. Those are the movies that I just showed you. All right, so they were very quick and they went and published this thing, JFM. And so they basically characterized the drift due to non-braking and braking on deep water packets, basically. And they're basically saying, essentially, wave breaking actually generates more transport at the surface, but otherwise, it's no different. And so they calculate this thing. What is this thing here? Okay. So what they do is they calculate. This is the key findings that they get from this numerically generated transport. So this is transport normalized to the phase speed. And forget about what S is, has something to do with, it's a parameter that we're modifying, basically the intensity of how we beat this thing, okay? And basically S here, it's essentially amplitude squared divided by something, okay? So basically at this point here, they say there's a phase transition. In transport, as you can see, the transport here looks very much like what Stokes drift is. And then once it starts braking, which is about here, you get an intense amount of transport. That's what they get. Okay? And they basically say, look, there's even a phase transition. Now, actually, so we said, that can't be the case. What happens is this is Longet-Higgins theory, and this is not. It's really not a phase transition. It's just simply a curve that smoothly transitions from here to here. And we can explain it. So there's no phase transition. Now, the proviso is that our explanation does not cover the particle flow at the particles that are actually disengaging from the fluid flow, the ones that are no longer continuous, we can't say anything about. But up to that, anything below that, we can say a lot about. So we don't get everything, meaning every particle in the system, but we get most of it. And so we have an explanation here. And the explanation goes back to this averaging procedure and what it breaks down. Okay, so this is what Longet-Higgins would have been doing. He takes the velocity field and writes it out as an expansion here, and then he starts averaging over waves, okay? Now what happens is, if you have this part here is associated with a current, okay? So you can ignore it completely. This is the lowest order wave and the correction on that, okay? Now, even if you have a stochastic differential equation, what you get is your expectations at lowest order of the wave is 0, as it should, and the non-zero part starts at the first non-zero asymptotic. And what happens is, in the Longet-Higgins case, this average is equal to 0. It just winds up being that way. You're looking at sines and cosines and so on and so forth. This thing here is 0, identically. Now, the reason it's 0 here is because you actually assumed that when you're looking at particle displacement, the displacement is very small compared to the period of time. But what if you remove that assumption? If your particle doesn't go back to something close, but actually winds up very far away, that assumption is broken. Okay, so this thing is non-zero. Oh, sorry. So in the standard Longet-Higgins theory, you get the current and you get the Stokes drift. But if this thing is not 0, this expression is incorrect. Okay. So that's what happens. So for transient waves, you say, well, okay, that term can't necessarily be 0 because you can have a particle go very far away. So you have to carry it along. And what happens is this curve, what happens is if you include the currents, if there are imposed currents, and you make this non-zero, then what happens is you get a smooth curve that actually, not showing. Okay, there's a curve underneath here that kind of goes like this. Okay, and it's actually this plus this, and it goes like that. Okay, and it explains it very well. So the moral of the story is, even if you're famous, don't publish soon. Especially if you're famous, they're not going to review it carefully. And the third thing is listen to your collaborators. So they didn't, so they went and published, and so basically their paper is making a false claim on a physical thing because they didn't understand the theory. Okay, and so if you do the theory correctly, this is all very well understood, and we can actually capture everything very well. So this is a messy looking thing. How do I explain it? Okay, so these are the actual orbits that you get under these waves. So as you can see, they're very complicated looking things. And in the interest of time, I'm not going to try to explain very much. The short of it is this. In all these cases, this is one single case, but it's at different times. Okay. What we can do is you can explain all of these particle motions, even if the wave is breaking, except we can't describe the particle motion at the breaking thing. So if it's part of the spray, we can't do anything. But up to the spray, we could get it right on the money. Okay. So the story is, this is showing you, red and blue is showing you the very long displacements that occur because of transient transport. The transient transport produces a lot of stuff moving a lot if you just prepare in the same way, a very careful way. But it could also produce just as well very little transport. For example, if you're just shaking it around in a very random way. But anyway, we get, these are all generated by our theory. We get it, we nail it. Okay. So there's nothing, no phase transitions, no mumbo jumbo, no nothing. It's just, it helps understand. Okay, I'm going to go to a different topic if I have time, or no?
11.
Okay, so let's stop on this one. Any questions on this particular topic? Yeah.
On the effect of shearing current, the way,
Yeah.
as well as the effect of Doppler shearing.
Yeah, so the answer is yes, but we do it as an additive thing. Basically, we say, look, if there is a current underlying everything, the averaging will not kill it off, right? And so it just survives. So it goes in as an additive thing, okay? And so I think it shows up. So that's this term here. Where is it that I have my asymptotic expansion? It's okay. So that's this thing here. And this can be shearing, it can be doing all sorts of things and so on and so forth. So if you take, now when you compute things like vorticity and so on and so forth, you're going to take the vorticity of this whole thing. Turns out this is vortex free if it's Stokes flow. If it's transient, it does have vorticity. Okay. So that's another thing that happens in transient flow. Vortical things happen, right? Shearing and all sorts of other things. So that's what I'm saying. If you're an experimentalist, you want to do something new in wave current interactions, focus on making measuring or making experiments on this transient transport, and it's open, it's wide open. There's lots of careers to be made on that.
Sorry, I got the question.
Yeah.
Concerning your the results that looked like in 2017,
yeah.
That transition, is that somehow reproduced by a couple models like ROMS you mentioned before, or just the
Yeah, so ROMS cannot do that because ROMS is based on the
that coupled with I don't know, phase average model or whatever. So I think
no, I don't think so, because everybody makes this, well, if the code is sophisticated, it includes the wave generator transfer, which is just the Longet-Higgins expression, so this is our thing, and that, or it doesn't include it. Now, does it include other things? No, I don't think, I have no idea if there's any, because no one actually thought of this way, transient problem.
Yes, so that could probably means that when you run couple model in the coastal area, somehow the transport is underestimated when
Yes,
waves start breaking.
precisely.
Technically break.
Precisely, and it's not modeled. If there is no model in it, you're going to underestimate it. Now, there's another thing that happens. I didn't want to show you these things. So there are models for rip currents and things of that sort. So if you do rip currents without wave generator transport, you get these rip currents that are unusually, they go very, very long distance. You say, wait a second, they don't go out 100 and, let's say on La Jolla's coast. You say, wait, my rip current should go out only 30, 40 meters, the strong one, you know. But if you do the computation, you get these rip currents that go out up to 250 meters out or whatever it is. Now, if you include the wave generator transport, then they get shorter. So it actually suppresses some things, right? But this is all steady state flows, longshore currents, rip currents. But if you look at now storms and this and that, none of that is covered properly by the standard theory. The new theory would be this transient thing where you don't average out this thing. Okay. All right. So let me go to another problem, which I call sticky waters. Okay. And okay, so here's a picture. This is this is a better picture. Okay, so this is the Oregon coast, and I think you have seen, for example, you get this sort of froth out of distance, and it kind of parts itself there, right? It sort of kind of generates it, and it stops there, and it kind of sort of lives there, right? And I often thought, well, why the hell does it stay there? Well, most of it is because you say, oh, that's where the wave breaking occurs, but nope, wave breaking is here, not out there, right? Okay, well, maybe there's some focusing something or another, right? And so it got me thinking that maybe there's something that, you know, there's this foam that either kind of goes all the way out here and it sort of stops here, or foam that might be brought in and it stops here. But basically there's foam, it gets generated somewhere else and it focuses there. Now you can also possibly imagine or have seen junk and crap and pollution and everything. It starts going towards the coast and kind of stops somewhere sometimes. Sometimes it gets all the way to the coast, sometimes it doesn't. So I call this sticky waters, okay? And the question is, why does this happen? Now, my model was initially going to explain, for example, this is just the red tide in Florida. And the red tide goes all the way up to the coast, but not quite, right? It stops somewhere. There's something that kind of stops it from going all the way there. Turns out my model is not very good for red tide, but you get the idea. There's something that says if this thing is constantly getting wave generator transport, it should get to the coast, right? I mean, it gets smaller, the transport gets smaller as you get closer, but it has to get to the coast. So why the hell doesn't it get there? Okay, so here's an attempt at an explanation. Oh, I had a movie of this, but I didn't upload it. All right, so let's think conceptually of our little channel, and we're going to include the fact that we got a shelf, okay? And now we're going to look at just simply a two-dimensional flow, or you can think instead that we're averaging out so that we only get 2 dimensions in flow, right? Depth and forward and back. That's it, okay? So we're sitting over here, and we say, okay, what's the net velocity right at here? If I average over the depth, what would be the net velocity for this flow? Well, it's got to be 0, right? It's got to be 0 here. Why? Because it's 0 here, right? If it's 0 here, it's got to be 0 here, here, here. So it's 0 everywhere. This is a two-dimensional case, right? Fine. So that is a constraint. The flow average over the depth has to be 0. Okay. Now let's assume that there's a region here. Let's say the stuff is coming in and it's going to park itself somewhere before some critical length L. Okay. Now the other thing I'm going to do is I'm going to take the junk that I'm transporting, the pollutant, and I'm going to say it's composed of 2 bits. One bit is the surface stuff, and the other bit is the stuff below the surface. Maybe it's of size p. Usually it actually dies off exponentially, right? So there's lots of stuff on the surface, say it's buoyant, and then there's a depth p, which has significant amount of pollutants. It can go all the way down, but let's say this is okay. And P is not going to change in depth because it's related to the buoyancy properties of the pollutant, and it's going to hit this bottom right over here. Okay. Now you say, wait a second, but so if it's average 0 here, how the hell do we get anything coming to the shore? Well, you got to break that. And the break there is that you get a non-zero average because if you look at three-dimensional flows, you can get stuff going like this way, right? And so therefore, if you look at a 2D plane, then it's not true that it averages out to 0, right? So if the flow is symmetric, the average is 0. All bets are off. You could not get stuff going to the shore. But it turns out it's not 0 because it's a three-dimensional flow, so stuff can go, stuff can go this way, make the way out, but there's fluxes in the non-orthogonal to the plane. Orthogonal to the plane. Okay, so here's a model, transport model. S is the surface stuff, and C is the concentration over the depth. So I just simply, for practical convenience, I'm separating stuff at the surface from stuff in the interior. But all it is a transport equation. It says it transports like so, it diffuses, and there are mass exchanges between the surface stuff and the bottom. That's all this model has, nothing more, okay? And notice here, we got the Stokes drift in here. And this thing here is basically a shear stress, wind-generated stress. Pretty simple, okay. All right, and we don't have sources or sinks, no evaporations, no nothing, so it's very simple. And what we want to do is we want to say, what conditions will prevail so that you get a situation where water will stick where this transport stops. All right, so what happens is we do some averaging. I like to average things. So, and you get these reduced transport model equations, which essentially are, right, diffusion, advection, and then interactions, okay? Now B here is the depth average, zeta is the depth of this, let's say this tracer B. So little b is tracer B divided by a depth, but it's a very strange depth. It's a depth that actually assumes is the bottom topography or is the layer of thickness, okay? So, but it's a depth, right? And then, okay, R is some, oh, where's R? R is equal to I. Okay, sorry. Okay, it's just simply the interaction stuff. Stuff that's not on the top is in the bottom or otherwise. That's all it is. Okay, so this is the key thing, is this term here. It's a depth that is the bottom topography, and if it's not the bottom topography, it's the depth of the concentration of stuff. Okay, so for example, zeta would be here H, and then, oops, right, at this point, then it becomes P. Okay. So now if you actually depth average using that notion of depth, you're getting an equation that is a lot more interesting. And it's an equation that has a velocity here that includes the bulk velocity and another term here that depends on this depth thing here. And it is multiplied by the diffusion. Okay. So we got a very different looking velocity, right? The old intuition was that it's just this, but if we do this carefully, we get another component to the effective transport of the bulk stuff. See, the surface, it doesn't change, but in the bulk it does. And that's the thing, when these two terms are 0, the stuff on the bottom doesn't move. Okay, so what happens, when does that happen? It happens exactly at that point. Okay. So basically what it says is the following. If you do this very carefully, you get stuff, you store it towards the thing. If the layer is very, very thick, there'll be a case in which it gets to a certain point and it will not get transported by the waves. Now it could get to the, but the only way it's going to go from here to there is through diffusion, not through advection, but only through diffusion. That's it. And you might say, well, you know, actually, I've seen that plenty of times. That should be the way it is, right? There's a depth at which waves don't generate transport. You still have to get the stuff to the shore. How does it get to the shore? At that point, it gets it through diffusion. Okay, so here's our bulk average velocity, right? It has two terms in it. It's got the usual stuff, but then it depends on how h and zeta look like each other. It goes to 0 when that happens, right? And now what we do is we look at a case in which you have, this is just an example calculation. D here is the diffusion. I make the diffusion. Okay, this is the distance from to the shore. Shore is at 0. This is 1,000 meters for whatever reason. And this is a diffusion thing. And we're going to say that there's a lot of diffusion at close to the shore because there's wave breaking. Okay? But it's low otherwise. Okay? And now what I'm going to do is I'm going to look at how the bulk velocity, actually this term here, depends on distance. And when the layer P here is the depth of the layer, when the layer is big, P equals 10 meters, then what happens is the velocity goes to 0, some distance away. So at 200 and something meters away from the shore, the velocity completely shuts down. If we get stuff getting to the shore, it has to do it through diffusion. Okay? Now, what's the other thing that it says? Well, when the layer is very thin, you can get stuff to the shore. Now you think, okay, suppose you have an oil slick and it's coming towards the shore. What's the typical thing people do? Well, first of all, they put barriers, okay? But the other thing they do is they make the water very choppy, thinking, okay, if we make it choppy, it's going to stop it. This said, no, don't do that. Do the opposite. Make it as calm as possible. That's what you want. If you make it choppy, you're going to make things worse. So this is actually against standard practices in oil disasters. So here are some results for this particular model. So I'll end with this very quickly. Okay, so this is a case in which there is very little, this is all wave-generated transport. So you get stuff in space starting here 500 meters, and then in time, it kind of gets to this point, but basically all the stuff gets to the shore. It all gets very fine to the shore. Now, as a function of the depth, as I said, there's a stopping. So here it gets to the shore because the pollutant is just simply occupying a very small bit of layer. But if the layer is thick, for example, if you make it really choppy, then what happens is it sort of stops, but it diffuses in. Okay? So that's basically the result of this thing. And so that's what I call sticky waters. The stuff will start to linger some distance away. All right, I'm going to stop there instead of showing you more of these things. Yeah, let me stop there and say, okay, are there questions about this particular thing? Yeah.
It's just that we're assuming that the water properties are not changing going offshore, but in reality, just thinking to temperature or salinity.
Yeah.
There is something except diffusion that could modulate.
Yes.
Did you do a scale analysis or something to see how it could work?
Yeah, no, I have not. Now, let's say if it has to do with salinity as opposed to anything else, or temp. Well, no, let's consider salinity and temperature. Yeah. I would say what that's going to change in this regard, but I didn't consider it because, of course, you can see this is a very conceptual model. What will change is this D. Okay. So what it's going to do, and so therefore D will affect my results in the sense that it's going to affect when this U bulk and this term here will zero out. Okay. So one way these don't zero out might be because D is so messy looking that it just never zeroes out. So that's entirely possible, yes. But that's where it would show up. Yeah.
Can I ask about that second term in the velocity?
Yeah.
Like, it's hard to, like, the first term is basically your Stokes script.
Well, it's just, the bulk.
You bring in,
Yeah.
what, like, it's hard to understand physically what that is in terms of the motion itself.
Yeah.
And is there any, like, any understanding of what the mechanism is? Because I guess really what you want is that B to zero out. So when those two are equivalent and opposite, they cancel, and then
Correct.
your stuff stops.
Stops. Yep. Yeah. Now this is because this velocity is a depth average velocity. Okay. When you're depth averaging, then you get integration by parts brings in new terms. So that's how it happens mathematically, right? You're just integrating very carefully, and the integration by parts gives you all these terms. That doesn't tell you what it is, but it tells you how it happens. Okay. So that's where it is. So again, all you want here is it could be a three-dimensional flow, but I'm always going to be depth average, right? So this is what happens. To see all these effects, you have to depth average whether you're in a 3D flow or 2D flow. Okay, fine. And in a depth average sense, you get this other term. And here, the interesting thing here is this is a derivative of, let's see if I can get a picture back. Okay, yeah. So, okay, so that's the definition of zeta, right? And zeta is just going to be h, so nothing interesting happening. And then as soon as it hits this point right here, then it becomes p, right? Okay, and so what is this? This is diffusion generated transport. It's the anti-symmetric component of the stress tensor, is what it's basically, right? There's a symmetric part, which is, the standard diffusion, and there's another part, which is the anti-symmetric, which has complex eigenvalues, which means it's a velocity thing, right? So when you're doing dispersions of things, you always have to look at diffusion, symmetric diffusion, and the other stuff that moves things around, it disperses things around. Be careful with the language. I got thrown into a detergent seminar because they saw dispersion on my title on my slides once, and I'm like, I don't know why I'm talking to you guys. You all talk about detergents, but I'm here to talk about dispersion, as in dispersion of particles. So that's what that is. It's the anti-symmetric component of the stress tensor. Yeah, that's the part that we don't get very well in all ocean transport, right? We're always we look at buoys and this and that. We look at what you get for transport, and you always get it wrong. So that's the complicated part. All right. So anyway, any questions? I'm finished, by the way. But if you have any questions on any of the material, be happy to respond to them.
Okay.
Yeah. As a former musician, I learned you never overstay your time. So I have to end on time.
Okay.
Rolled it? Oh, one more?
Yes,